Okay, good morning. Today we are going to talk about the midterm. I hate midterms. They take a lot of useful time away. We could talk about circuits instead of solving silly problems. But, you know, there is also we could cancel it. But there is also one good thing about midterms and exams in general, and that is that while I'm sure that most of you totally agree with me that circuits are about the most interesting thing that we can study, and therefore studying for them just the motivation goes just on its own. There are perhaps still a few of you that need a little bit of more motivation, and so we have the midterm, and we're not going to cancel it. But anyways, what we talked about so far were resistive circuits. So there are circuits with resistors, and there are also sources, and also operation amplifiers. We talked about those over the last 2 weeks. And so those topics are going to be on the midterm. Now, in general, we have only one more lecture on Wednesday before the midterm. I'm going to talk about something else. I'm not going to ask anything difficult about the midterm, but please come to the lecture. It could be that there is a quiz question on the midterm about that stuff, right? So just pay attention. There's not going to be anything difficult about something that is beyond today's lecture on the midterm, but just Wednesday's lecture, we cannot just blow it off, right? It's important what I'm going to talk about that. There also, we're going to use it in the future. Yeah, now we already have a question. Yeah, isn't capacitor on the So again, that's what I just, so Wednesday we're going to talk about capacitors. I could ask you, what does a capacitor store? Well, George, and I will tell you on Wednesday, and you should be able to say that then. So please come on Wednesday. The material that we talk about on Wednesday will be covered in depth in midterm 2, not in midterm 1, right? Logically. All I'm trying to ask you is to please come nevertheless on Wednesday, turn on your brains, pay attention, because it's ultimately, of course, going to be on an exam, and I don't want to repeat it. Okay, so but with that, we will focus today on the main topics that are going to be on midterm 1. And we're going to solve a bunch of sample questions that are just like the ones that actually are going to be on the midterm on Friday. I also, before I forget it, I want to say that the midterm starts at 8:30, not at 9 o'clock. I sent you an email about that. It's also announced on B-Space. And the midterm is not going to be in this room. We have 2 other rooms on campus. One is North Face or something like that. Anyways, it's on the website, and you can look it up on the maps that are on the university website where you have to go for the midterms. Okay? Okay? All right. Okay, so first of all, I want to give you a perspective. I'm not going to ask about this perspective about the midterm, but nevertheless, I want to say that because this is really the reason we are going to do this. Right? Obviously, the midterm is going to be 4 or 5 somewhat silly problems that you can solve in 1.5 hours, right? Or I hope that you can solve. But that's really not why we are here, right? You're not here to solve midterm questions for the rest of your life or something like that. It would be very silly. The reason we did all of this is that we talked about sensors, resistors, op-amp circuits, stuff like this. And what can this do for us? Well, we can take a sort of simple phone that operates just fine as a phone. You can talk on it and so on, and talk your ear off or whatnot. But you can add these kinds of things that we talked about now for the last 4 weeks or so. You can add them to a phone, and then you get the so-called smartphone, right? That has sensors in it. It knows about acceleration. It knows about light. It knows about orientation, and so on and so forth. You will have perhaps other ideas of things that can be added to a phone to suddenly make it not just something to talk, but something that is much more useful and practical and has many more applications. Okay, so that's really why this is about. Now, we cannot always talk about why. We also have to talk about how, and so that's what we're gonna talk now. And of course, the how is also a little bit just what in the world is going to be on the exam. So I've already, throughout the lectures, I already given you these sheets that say, at the top they say skills. Those are the kinds of things that I expect you that you actually carry away, that you actually learn. And I summarized those on just 3 or 4 sheets here. So it's the same thing as you've seen already, right? Here, the sort of basic concept we talk about, that this is really an approximation that we are using here that is very useful for lots of applications, like the ones we just talked about. Electronic circuits work with charge, voltage, current, and so on. Right? You know about that stuff. Then resistive circuit analysis, we looked at lots of different ways on how we can understand and analyze resistive circuits. Why did we do that? Well, again, because ultimately, as we want to design them, we of course need to know how they work, and we need to be able to determine whether a circuit that we invented actually performs the function that we expect it to. All right, so there's a list of topics also that you just need to be familiar with in order to do well on the midterm. And then finally, operational amplifiers, right? We found that they are kind of bizarre things, right? They have infinite gain, but then if we add this wonderful sauce called feedback, then we can make them do all sorts of very interesting things. And so here again, I have made a list of the kinds of things that we do with operational amplifiers and that you need to be familiar with. And again, ultimately, why do we do this? Well, we want to design circuits, and so here I've listed a few of the things that go into this. So first of all, we need to be able to describe this wonderful world of electronics with its language, and we use circuit diagrams for that. Well, I just added this, right? There is always this danger that I ask something that to me it looks really obvious, right? Like, well, 110 volt comes out of a power outlet, right? I expect that you sort of know that. Maybe we haven't formally covered this in the class, but sort of common sense also, right? For everything engineers do, we also need common sense. But then what circuit design really is about is we have some kind of a problem we want to solve, and then we have to come up with the circuit topology and component values that meet the requirements set by our ideas. Okay, and so I give certain examples here. For example, a divider, right? Given 5 volts, you want to make a reference of 3 volts out of that, and we can do that with a voltage divider. And there are a couple of other examples. So let me let's go over a few practice examples, actual practice examples for the midterm. So here is the first one. And again, this is now a little bit contrived, right? That's not really circuit design, but we may come up with a circuit like that, and then we want to figure out what function it actually performs and whether it performs the function that we intended to perform. Incidentally, all of this is also on the website, and you can download it from there. Okay, so, well, all right, when we have such a circuit, there are lots of ways to approach it, and it's very important, especially in an exam, that we use a systematic approach on how to deal with it. Now, it turns out that this is a pretty simple question here, so some of you already may know the answer. I don't want that you give that answer just right now, but what I would like to know is, how would you approach this circuit? How would you go about solving this problem, figuring out what is the value of that voltage Vx here? Any suggestions on how you would start? Yes? Okay. First, simplify the circuit. Well, source transformation is one way to do that. I would say that there are even simpler simplifications that we could do. Any suggestions? Yeah.
Would superposition work?
Maybe. But let's stick with that simplification, yes. Okay, yes, this is correct, and if we can see that, then we actually can solve this problem in 1 minute or less, actually, probably in 10 seconds, right? But some of you probably, who has not seen the solution yet for this problem? Hey, give me a break. You have all seen the solution for this, because if you have all seen it, I'm going to do this. You want me to? Okay, so, but then please answer my question reasonably, right? I ask my question again. Who has not seen the solution for this problem yet? Okay, there is at least sort of half. Okay, that's fine, right? So that's why we go over this. So now we want to understand in a practical way on how we go about this for somebody who has not just seen the solution, right? Yeah, so several of you have, yes? The what? Yes, I changed one or two components perhaps, or I asked for something. Yeah, it's actually the problem from the quiz, but I modified it very slightly. Okay, it's not the quiz problem. Yes, so I because I figured that the quiz problem by now everybody has figured it out, and so I'm not going to talk about the same thing again. At some point, everybody gets bored, you and me. Okay. Yeah. Okay, so that's if you see that, then that's the solution. No, but again, if you're not very smart, well, I mean you're all very smart. But anyways, if you haven't, if you don't just see the solution, just do something reasonable first. Well, something reasonable, for example, what about this resistor R1? Does it matter? It doesn't really matter, right? This guy, it doesn't really matter. We want to know node voltages here. It really doesn't matter what the value of that resistor is. The current flowing through that branch is I2, and we can change that resistor to any value, and the current still is I2. Okay? What about the resistors R4 and R5? Well, we can combine them into one single resistor, and then we see that they're actually in parallel to what? To the voltage source V1. So these guys really, they don't matter either. And then these guys here, well, they could matter, and they probably do, but we can replace them by a single resistor R26, which is simply the sum of the two individual resistors. Once we have done that, so I mean, this is how I would look at that, right? I haven't seen the solution yet, and so I say, well, gee, you know, this is really too hard a problem, harder than necessary. Let me make it a little bit easier first. And then once I've done that, I have now a pretty messed up circuit diagram. So the next thing I do, and it takes very little time, I just redraw the thing. And you know how to write more nicely than I can, so you write it more nicely. So this is R3, this is R26, and then we have this voltage source V2, and this is I1, and this is I2, and then finally we have also the quantity that we are actually interested in was this Vx, and maybe just for convenience we call this ground. It doesn't really matter. Okay, so now we have a problem that is still we have a problem that is still not totally, absolutely trivial, but it's a lot simpler, right? So if I'm in an exam and I'm a little bit nervous or so, what do I prefer? Do I prefer the circuit at the top, or do I prefer the circuit at the bottom? Well, of course, the circuit at the bottom is much preferable, right? And so the transformation really getting from the top to the bottom is quite simple. So I can do that even when I'm nervous, so why not? Okay, so now we can solve this in many different ways, but now perhaps, well, one way actually I could solve this is I could try to use node voltage analysis. Then I would have here an unknown voltage, and what about this one? Well, gee, there is a floating node voltage source on top of it. But I see that the other side of that voltage source is also connected to a voltage source. Well, gee, I actually know the voltage here. This is V1 minus V2, right? And once I've seen that, it's trivial. And if you did actually this, if you approach the problem like this, then you also can figure out the voltage across or 26. Actually, you know it now, and you can solve the problem from the quiz, and which is why I pushed back on those of you who said, hey, you know, the quiz was very unfair. If I had half an hour longer or so, I could have solved the problem. That's really not the point. Right? If you approach the problem right, like circuit designers can solve it rather straightforwardly. So we actually don't even need to, even this, the voltage here is no. But now if we look at this node, we see that actually the current flowing into the node here is known. It's I1 plus I2. Well, in that case, what's the current here, flowing here? Well, it's I1 plus I2. And consequently, Vx is equal to R3 times I1 plus I2. Now, of course, once I see this solution, I can go back to my original diagram and I see, well, yeah, of course, that's what's happening here. These two currents simply go into my resistor, and then I can use Ohm's law to figure out what the voltage is. Do something like this when you solve the problem. Then you can also solve it swiftly. Okay, you will recognize this also as being somewhat similar to the second quiz. All right, so the question here is, again, what is this voltage Vx? So, again, there are many ways on how to approach this problem. We need to use an approach that doesn't require us to know the answer beforehand, because, again, some of you, they will see the answer right away in a problem like this. But if you don't, then what, right? So what could we do? This is an operation amplifier problem. What could we do about solving if we don't know the answer, right? We're sort of a little bit lost still. What are we going to do? Yes, we could simplify. Yes. Write down the equation for an ideal op-amp. Yeah, you could write down the equation for an ideal op-amp. And if that helps you, no problem. But on the other hand, you know, I mean, that's kind of... maybe that is a little bit too little commitment to the actual problem. Yes?
There are several useful source transforms we could take in this problem.
That's true. That's true. We could use source transform. But hey, you know, this is an operation amplifier problem. And one of the nice things about operation amplifier problems is that when we have negative feedback, then there is an interesting condition met about some node voltages. Yes?
You can notice that since it's negative feedback, the voltage at the two inputs is the same.
Right, we figure out first, hey, you know, this is an op-amp problem. Why is it good to start that way? Well, because then we know some constraints that may be helpful. Yes?
I'm kind of confused. When is something negative and positive feedback? Is there some path from the output to the positive terminal as well?
Yes. So I'll address this. I'll address this. So okay. So this is a feedback loop, and this is negative feedback because it goes to the negative terminal, right? So we agree on that. So your question really is now, why isn't this also a feedback loop? Okay. So this is a little bit more subtle, and I'm going to give you an explanation. But I also give you another. I tell you one other thing. On the midterm, I make it very clear. If there is a problem with positive feedback, I make it clear that it's obvious to everyone that it's positive feedback. Okay? It's a good thing to be able to distinguish positive and negative feedback. It's a good thing to be able to determine that the yellow thing actually is not a feedback loop. It is sort of on the borderline of EE40. If you are aspiring for an A or an A+, you should be able to deal with that kind of subtle insight. If you want the B or even you probably don't want something less than that, right? But anyways, if you're not planning to become a circuit ace, then the explanation that comes maybe follow you a little bit, and that's okay, right? Not everybody needs to be sort of a super circuit designer. But the reason why this yellow thing is not a feedback loop is really feedback is defined as the, let's call it F. Feedback is defined as the quantity at the opposite side of the feedback loop. Let's call this Vy over V out. Okay? It's this ratio. All right, now this node here is actually connected to ground. So any change in V out, of course, causes a current flowing through R7, but that current disappears into that ground node, and the voltage here is always going to be zero, totally regardless of V out, of what V out is. And therefore, the voltage at V4 is also going to be totally independent of what V out is. Okay? And so this ratio, therefore, is zero. And even though that loop somehow exists in this circuit diagram here, because it has a gain of zero, really, Vy is not affected V out, and consequently there is zero feedback or no feedback applied.
Would that be zero or undefined? Because like Vy over V0 could be some number. It just doesn't, what you're saying, it doesn't matter. Like because there's a connection to ground, right? Like,
well, actually no, it really is zero. If changing V out somehow changes Vy, there would be feedback there. And would be important to consider that.
That means the derivative is zero, not the actual.
That's right. I would have to set all the sources to zero first in order to figure out that ratio. And otherwise, you're right, it's the incremental change. Something incidentally, these derivatives you're going to talk about for always and ever in EE 105, it's a very important insight. It's not something that we're going to talk about in EE 40, okay? So I already put the first one of you asleep, right? This is good stuff to know about circuits. It won't be on the exam. If there is positive feedback, if a feedback loop is negative, go and look for it and so on. That's good to do. But it will be negative unless I make it very, very clear in the exam. GSIs, please listen. So make sure that it's clear. Right? The GSI, I make the midterm, right? And the GSIs check it to make sure that I haven't overlooked something or inadvertently made a problem that really is not fair and is not appropriate for you to solve. So look for that feedback. But unless I made it very clear that it's not negative, it's positive feedback, you can safely assume that it actually will be negative feedback. Yes?
I have a question about the negative feedback.
Yes.
Problem. So isn't it a bit dangerous to just blindly assume that the two terminals of the amplifier have the same voltage because there is a voltage source at V2 inverting terminal?
Yeah.
Use the voltage from V0 to some other number.
Okay, so that again is a little bit of insight. So that's a good straight that you have here. Right? You say, we did that for simple resistive feedback, and then we use that to determine there is negative feedback. Now I introduce suddenly a voltage source in the feedback loop, and does it still apply, and so on. That's a good thing to ask that question. And if you really want to know the answer, go and solve the problem, assuming that the op-amp has a finite gain, solve the whole thing, and then let that gain go to infinity and see whether you get the same solution, whether you actually get that the voltage Vx and Vy, whether these voltages are identical. Okay, so that would be the way to investigate that. I would say that in the midterm, don't do that because it may take you a little bit longer, right, to solve it that way. Although even that might be actually, for such a relatively simple problem, it may be okay. But it turns out that in this particular case, the negative feedback and Vx equals Vy and so still applies. I'm not going to pull your leg on a. Yeah, I mean, I get a lot of emails about, are you going to ask us about dependent sources and so? I'm not going to ask you about stuff that I didn't talk a whole lot about. It turns out an operation amplifier, of course, is a dependent source, and so I'm going to ask about operation amplifier, but I'm not going to talk for 5 weeks about something and then I go and ask questions about something else. Really wouldn't make any sense, right? Then I'm just going to prove to you that I haven't taught you a thing about what I asked about. Why would I do that? I'm not a masochist. Okay, so yeah, so Vx and Vi, they are actually the same, okay? And so if I want to know what is the value of Vx, then that may be a slightly hard problem, but it's actually the same problem as asking the question, well, what is the value of Vy? So could we possibly figure out what is the value of Vy? Well, and it turns out that is trivial. It's simply R3 times I2. So now we have Vy. And we can, of course, write this down now in a blink of a second. Yes? Okay?
I was pointing out that
Okay. All right. So that's how we solve this problem. So of course, if in this problem you were to go and apply node voltage analysis, ultimately we get the correct result. It will take you probably half an hour or maybe even more time. It would be a technically correct solution, but you would have approached this problem not like a circuit designer, but like a mathematician or like a computer. And I mean, it's laudable and it's useful if you can do that, but this is not the way to become a circuit designer. So in EE40, we want to develop some of the insights and skills that allow us to actually be circuit designers. And so the quiz sort of insisted that you approach this problem like a circuit designer, not like a mathematician. Okay? So in fact, I could say that just about all these analysis problems that we solve in EE40, they can be solved using a computer and the program SPICE, right? Obviously, the point of this course is not to teach you to behave like computers, right? All right, so let's go on another example here. Again, we want to know what is Vx. Hey, that's sort of becoming repetitive. And there is no op-amp here, so again, what are our choices to sort of practically approach this circuit? Well, first of all, we can make some simplifications, right? We can get rid of this guy here. We also really can replace this with one resistor R56. And then what we really need to find out is this is an unknown voltage here. We need to solve for that. This is an unknown voltage. And this one here, it's actually a known voltage, and we probably conveniently put the ground here. At this point, we have two unknowns, let's say V1 and V2. We could, of course, now use node voltage analysis. We would find the values of V1 and V2, in particular V2, and this well, I should have called this VA and VB, right? And this node voltage here, V1, we already know, and then we can use a voltage divider equation to figure out what is Vx from knowing V1 and V2. Okay? So that's how you would do this. Again, by simplifying the problem a little bit, you got rid of this node here, and you got rid of this node at least for solving your equations. Okay? And then afterwards you introduce it again. That's a simple after step, doing the voltage divider. Yes? Well, again, I mean, for example, the resistor R4, why can we discard it? Well, the node voltages, the things that I marked in yellow circles and boxes, they really don't change if I change the value of resistor R4. The node voltage here in the middle, this one, of course, depends on the value of R4. But if I, for some reason, wanted to know what that value is, it would be trivial to figure out. Once I know VA, then, of course, I know the current through R4. It's I4, right? And I know that, therefore, the voltage drop across R4. It's trivial to figure out what that voltage at that intermediate node is. Likewise here, right? R5 and R6, of course, I happen to want to know just the voltage in the middle between these two. But that really, once I know the voltage on either side, then I only need to apply a voltage divider. So there is kind of a trade-off, right? Either I have one more equation in my system of equations and unknowns, right? And can solve for that. Then I get the answer directly in one step, but I have to solve 3 equations, 3 unknowns. Or alternatively, I can break up the problem into 2 steps. I solve 2 equations with 2 unknowns first. I get VB, and then I apply in a second step now my understanding about voltage dividers and figure out the voltage in at that middle node. And I personally, I much prefer solving just 2 equations, 2 unknowns. Okay. So it turns out in this problem, because you know the current flowing. Okay, anyways, I think there are perhaps some ways also to solve this problem more simply than that even, but with more insight. But I would say this is kind of reasonable, right? If you have a problem like this, if you approach it without any sort of circuit insight, you have 4 equations, 4 unknowns. You can solve that problem if you have good math skills in the 15 or 20 minutes that you have per problem on the exam. You have to be very organized. You have to start right away that path. But then you perhaps may be able to do it. But if you have just a little bit of circuit insight, well, you can reduce it to 2 unknowns, 2 equations that are much more easy to solve. And then definitely 15 minutes should be plenty. Yes?
Could you reiterate
how to find voltage VB? Okay, so what we're going to do is we're going to write now, these are our unknowns, VA and VB. We're going to write KCL equations. Right? You do node voltage and at the edge my tablet doesn't work quite right. So node voltage analysis for VA, for example, we get I1 plus VA over R1 plus I4 plus VA minus VB over R7 equals 0. And then likewise VB, we would get minus I3 plus VB minus V1 over R5, 6, which is the sum of R5 and R6, plus VB over R3 plus VB minus VA over R7. Now I have 2 equations. I can solve these for VA and in particular VB. That's what I'm interested in, right? Okay? That's all I have to do. These problems are not really hard. Of course, if you just start writing random equations or so, they may not get you anywhere, and it may take a very, very long time to find a path out of a spaghetti net of lots of equations, okay? So use some kind of a common sense approach, and again, if you have good circuit insight, then use that circuit insight to do minimal amount of math, but if your circuit insight isn't that powerful, well then do node voltage analysis, but stick with it and pull it through, and in the end check your result using one of the other techniques to make sure that it's right if you have some extra time left, okay? Important not to use some, oh, this is hard, so I sort of wander off on a non-productive path. That's usually where people lose points. Okay, here same kind of a problem. Turns out let's suppose that we really didn't want to take any risk and just apply node voltage analysis. Yes. Okay? Yeah. On my screens it shows this. Well, whatever. Technology isn't perfect. Okay, thanks for asking. Yes, so let's approach this problem 2 ways. The first solution is going to be, I'm like a computer. I don't want to think too hard about it because I'm nervous. I may make a mistake. I'll tell you a little example, just half a minute. I did this once. I was a first-year grad student at Stanford. I solved the problem. I thought, well, this is a little bit tricky. I'm not going to apply too much insight. I may get the wrong answer. And I simply used node voltage analysis, got the result, checked it, made sense, and then I turned it in. It took only half the time allotted for the exam. And the teacher, who's now a friend of mine, looked at it and said, this is wrong. And I was a little bit upset. And then next time I came to class, he said, oh, thank you. Actually, you had the right solution. I made a mistake. I applied all this insight, but then I somehow made a little mistake. So most of the time, of course, the mistake was mine and not the instructor's. But that's an example where it may be okay, right, on an exam to say, well, you know, I don't want to take a risky, a lot of insight, tricky kind of approach, but just apply a straightforward Node voltage analysis, inversing matrices, that's just mechanics. I can do that and get a result. Okay, so let's see how we would fare if we would do that here. So what are the unknown? What are the nodes? Well, this one is a node. Here we have a node. Here we have a node. And then we have two nodes, the two ones with crosses. Why did I put crosses on those nodes? Because how do we do node voltage analysis with operation amplifiers? Well, first of all, we have to check that it's negative feedback. I sort of skipped that step here, but yes, it's negative feedback. We have two negative feedback loops for the two different operation amplifiers in this circuit. When you have negative feedback, then the rules for node voltage analysis change a little bit, right? We have now one additional constraint, that is that for every operation amplifier, the voltage here is 0 and the voltage here is 0, right? The difference of these two voltages plus minus, yes.
You didn't put ground in this picture, so that means we can put it anywhere and it doesn't matter.
Actually, I should put ground, okay? Okay. Yes, I should put ground. All right, on the exam, again, GSI, is anybody here actually? Make sure that I have ground on the exams. Okay, so we have that constraint. So that gives us one equation additional for every op-amp. And if we then would write all the node voltage equations for all the unknown nodes, we would actually have one too many per op-amp. That wouldn't be so good. And so the way we take care of this, it turns out the way we have to take care of this is we're not going to write node voltage equations for the outputs of the operation amplifiers, okay? So that's it's probably best to remember. I suppose you can derive this also one way or another, but you will find out very quickly if you try to apply a node voltage equation to one of the operation amplifiers outputs. You will notice right away that you run into a trouble. What's the trouble? How do you know what is the current that comes out of the operation amplifier? We don't know. So fortunately, we don't need to write these equations. Yes?
Will there be any current produced by the amplifier?
Yes, of course, the amplifier, at the output, current is flowing, right? But no current is flowing into the input. Right? That's this funny thing because the operation amplifier, there is really sort of a ground terminal hidden inside, but we don't see it on the outside. Right? And in reality, in a real op-amp, it's really the current comes out of the supply, but because we don't draw the supplies, and then this charge neutrality business doesn't apply for the ideal op-amp. Right? So there is current coming out, but no current going in. Well, how is this possible? Well, it's not possible in a real circuit. In the lab, you have to hook up supplies, and then the world is back in order. Okay? So we could write now 3 node voltage equations. I don't want to do that, but that's the first solution, the first way to approach these problems. Perfectly okay. You will get the right solution. You have to solve 3 equations, 3 unknowns, 15 minutes. You should be able to handle that. So one way to do it. Now, let's also look a little bit with more insight at this problem. Well, this is the input here. Where does this current go? Does it flow into the op-amp? No, right? It has to flow here. Now, here it has 2 possibilities. Does it go into R1 or R2? For once, you're wrong. Okay. What's the voltage? What's the voltage here at this terminal that I just made the bubble? 0, right? The voltage there is 0. Therefore, what is the voltage across the resistor R1? It's also 0. There is no current flowing through R1. So all of this current, actually, this current here is II. Okay? So therefore, the voltage here is going to be equal to R2 times II, right? That's the voltage here. Okay? And now just a little bit more circuit insight, and then you see that this here is just an inverting, thank you, an inverting amplifier with gain R5 over R4 and minus that times R2 times II and that is equal to V out. And now we can divide by II, and we get the result. Right, so obviously this is a lot faster. If we can see this solution, it's a lot faster than solving the 3 equations. Your choice, right? But please, please do me the favor in the exam. Don't do something in the middle and then get lost, okay? Because I want you to do well also. After all, I spent a month trying to teach you this. I like to be successful just as much as you, okay? So please help me with that. Okay, so now the really interesting problem, right? This is really the kind of stuff we want to do. We want to be able to design something. So fiber optic receivers, where are they used? Well, who uses the internet? Well, we all do, right? How do all the informations get around on the internet? Well, most of them, they actually go over fiber, over glass fiber. We use a laser to turn our information into light, and then we send light pulses, photons, and they have to be detected somehow. How are they detected? Well, there's something like that solar cell. It's called a photodetector, a photodiode, that is at the other end of that glass fiber, and it detects how many photons are arriving. Well, it turns out that this photodetector can be modeled like a current source, ID, with an output resistance RD. And the little problem is that while the number of photons that come in produces a current that is exactly proportional to the number of photons, so ID is proportional to the number of photons, the value of RD varies all over the place. You really can't give a good value to RD. So we have to come up with a circuit that measures the value of ID totally independent of what the value of RD is, okay? Because RD is going to vary all over the place. So how do we approach this problem now? Yeah.
RD, is that in series or parallel with ID?
Okay, right. So that's a very good question. The first thing that we have to address is, well, here we have a current source with output resistance RD. How would we draw this in a schematic? Well, let's start with the current source. A current source, and the value is ID. Right? I guess everybody can get that for. Now we have this question. Well, we have a current source with an output resistance. Where should that output resistance be? Should that be in series with the current source, or should it be in parallel? It should be in parallel, right? Because really having a resistor in series with the current source really doesn't do much or anything at all, right? So that's really the circuit that we have. That's our photodetector. That was sort of given. We already solved the first part of the problem. We already got 1 or 2 points, okay? But now gets the fun part, and it's a little bit harder than getting more points, right? Okay, so well, now, hey, why don't we just try something? Here it may pay off to just try something. Well, we want to turn this into a voltage, and the voltage should be proportional to some resistance Rx. So why don't we try this? What is the voltage here, actually? Well, this voltage here would be ID times RD in parallel with Rx, okay? And RD in parallel with Rx is, of course, less than Rx, and consequently, it's not going to solve the problem just quite right. I mean, it's sort of a first step, and on exam, you may get another point or 2 partial credit, but that's about it, right? In practice, of course, this solution, your company goes bankrupt, it's not going to make it. Okay? Yes?
Buffer amplifiers?
Yeah, somehow that's a good idea. Somehow if we could use an amplifier, yes.
You can use like RD over RD plus RX times ID.
Yeah, we could try to modify this a little bit, huh? Yeah, exactly. The only problem is that these photodiodes, they are nasty. They don't tell you what RD is. RD varies, right? The temperature changes and RD is different. RD even changes when you have a lot of light arriving, then RD is suddenly smaller. How so? So you would have to know how much light you have, and then you have to adjust the value of RD. You can't do that. A billion times a second, right? That happens pretty fast, so that's not going to do it. unfortunately. So I like the other idea better if we somehow could apply an amplifier here. So what kind of an amplifier do we want? Do we want to have a high input resistance or a low input resistance? High? Low, right, low, because we want that the current disappears into that amplifier. Now, how do we get a low input resistance? Yeah, no, not this. Okay, so we want a really low input resistance. Well, let me get rid of this thing, and we actually did this somewhere on the homework, and I told you, well, look at the homeworks. They tell you a lot of interesting things, maybe even the solution to an exam. But let's. If I make an operational let me draw this a little bit low. If I put an operation amplifier here, this operation amplifier is going to have two inputs. What is the difference between the voltage between the two inputs? If I apply negative feedback around eventually. Yeah, here I have 0 volts, right? In between here I'm going to have 0 volts. So let me for the moment just sort of connect this down to 0. So now if I apply a feedback loop around here and I somehow connect this here, the voltage here is going to be 0. In particular, what is very important is that voltage is not going to vary at all anymore, right? The voltage here is always going to be 0. It's not going to change. And because it's not changing, the current through RD is not going to change. In fact, there is no current flowing through RD. Now I just need to somehow close my feedback loop, and well, let's try a resistor. What's the, yeah?
So if there's no current flowing through RD and no current flowing through the amplifier, how do you justify the current source?
It's going through RX.
Right. So we had to still, how do you do this design? I mean, I can tell you that I do it like that, and everybody, all designers that I've seen, you sort of say, this is a hard problem. Let me try something, right? And then I think, well, it doesn't quite meet the requirement, right? That RX just directly. And so little by little, I try, and then, oh, no, that doesn't work. Then I take it back, and so on, right? It's a little bit harder. And so this would be sort of a first design example. So that we can do. So little by little we tried it. So now actually turns out that we are not quite there yet either, but we can figure out what is V out here. V out is actually going to be equal to, well, what's the current? This current here, ID. And therefore, what's V out? It's 0 volts minus Rx times ID. Okay? That's what I have now, and that is simply because I typed too quickly and didn't think, but I actually asked here plus Rx times ID, so you need to have one more inversion. How do you do that? Yeah, just an inverting stage, right? And that is also something you can get a few points, right? So this. That's really the V out. And this one is OR, and this one is OR also. Okay?
Could we just put the ID current source and then get RX ID?
Could we just put?
Flip it so it goes down instead of up.
That's right. Yeah, okay, that's a good idea. That's a good idea. Yes, and that actually was totally left open in the question here, right? And so you can, after all, if it's not given, you can make the choice that is more convenient for you. And hey, good for you. Yes.
For this question, can replace the RD with RX, and then link this branch to the positive, and then there's no resistance for the negative.
Well, if we somehow could take away RD, right? And
Replace with RX.
if we this one here? Yeah, but how can we do that? This whole thing, that's our diode. It's made that way. It has this RD inside, right? I mean, lots of times, hey, if only we could get a diode that didn't have this RD. Well, nobody has invented one yet, yes?
How do you justify that there's no current that flows through RD?
Because the voltage across RD is 0. Yeah? Yes.
Any value between 20
And yeah, exactly. Anything between 20 and 80 kilo ohms. I could give you any other range, right? The point is that you don't know what RD is. It's not 0. It's not infinite. We would like it to be infinite, right? But it varies all over the place. Very often in sensors we have this problem. We want to know this quantity here, but there is some element that sort of makes it difficult to get at that quantity. All right. One more announcement. My office hours this week, it's on Tuesday, 5 to 6, not on Wednesday. On Wednesday, I'm on an airplane. And, well, I'll see you Wednesday morning.